Hello, thank you for watching this video. So in this video I'll be doing question 7, which is the electrostatics of November 2020 question paper, physical sciences. So let's get moving. So I'll read the question like I always do. I'll show the question so that you can pause, read for yourself in case you want to do the question first or you're not happy with my reading. So now let's go. Two charged spheres A and B are placed on insulated stands that are 0.2 meters apart, as shown on the diagram below. They carry charges of minus 4 times 10 to the minus 6 coulombs and 3 times 10 to the minus 6 coulombs respectively. Let me read this again. Two small charged spheres A and B are placed on insulated stands that are 0.2 meters apart, as shown on the diagram below. They carry charges of minus 4 times 10 to the minus 6 coulombs and plus 3 times 10 to the minus 6 coulombs respectively. So the two spheres, they are charged A and B. They are 0.2 meters apart, and A carries a charge of minus 4 times 10 to the minus 6 coulombs, and B carries a positive charge of 3 times 10 to the positive 6 coulombs. This is our statement. So you are told that point M, that one over there, M is a point that is distance 0.1 to the right of CB. So you are told that point M here is 0.1 meters away from sphere B. That's the information that you're told. Okay, let's continue. 7.1. First question. Let's read it. Calculate the number of electrons in excess on sphere A. So now they want you to calculate the number of excess electrons on sphere A. So now, how do you calculate the number of excess electrons on a negatively charged sphere? So it's easy. So okay, our number of electrons is equal to our charge, which has charge, the charge which contains the extra electrons divided by the electron charge. So now, sphere A is the one that have excess electrons. How many excess electrons are there? So we're going to say, okay, minus 4 times 10 to the minus 6 divided by negative 1.6 times 10 to the minus 19. Minus 19. So from this you'll get the number of excess electrons. So you punch it on a calculator. Say, okay, negative 4 times 10 to the minus 6 divided by negative 1.6 times 10 to the minus 19. So your number of excess electrons is 2.5 times 10 to the 13 electrons. So this is the number of excess electrons on sphere A. So we go to the next question. 7.2. Calculate the magnitude of the electrostatic force exerted by sphere A on sphere B. So they want us to calculate the magnitude of the electrostatic force exerted by sphere A on sphere B. Okay, so they want us to calculate the magnitude of the electrostatic force exerted by sphere A on sphere B, which is easy. This is Coulomb is equal to K Q1 Q2 over the square distance between them. So you use Coulomb's law to calculate the electrostatic force exerted by one charge to another. You know Coulomb's law. The electrostatic states that the electrostatic force between 2 point charges is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. So we use Coulomb to find this force here. So that force can be attractive, can be repulsive. right? So now in this case, because A is negative and B is positive, we know that this is an attractive force, or a force of attraction, right? Because they have different signs. So in this case, we say, okay, F is equal to QK, which is the Coulomb's constant, 9 times 10 to the power 9. Q1 is 4 times 10 to the minus 6 times the second charge, which is 3 times 10 to the minus 6 over the square of the distance between them. The square of the distance between them will be 0.2 square. Then F is equal to, punch this on your calculator. What do we get? Say 9 times 10 to the power 9 times 4 times 10 raised negative 6 times 3 times 10 to the minus 6, all divided by 0.2, all squared. So what do we have? Our force is 2.7 newtons. Attraction. So now, as you might note, I didn't include the signs on my calculation because the signs are telling us whether our force between these two charges will be attractive or repulsive. But we know that we don't have to include them. So now, in this case, because we know that these two charges are of different signs, so we know that the force between them will be attractive. So now, instead of making my calculation tedious and including the signs, I always leave them out. And then when I do leave them out, and then at the end I'll write if the force is repulsive or attractive. So in this case, our forces between point A and point B is 2.7 newtons, which is attractive. So the force that is exerted by sphere A on sphere B is 2.7 newton, that is attractive, which means now sphere A is pulling sphere B at a force of 2.7 newtons towards it. So the signs, I don't usually put them on my equation because I know they only tell me what kind of force will I be having. So that's why I leave them out. But if you want, you can include them as long as you will explain what will your negative answer mean. So, because now if your answer is negative, which means one was negative and the other was positive, so now that should be attraction. If your answer was positive, they could have either be both positive or both negative. So now your force will be repulsive or repulsion. So let's go to the next question, which is 7.3. What are they saying? Describe the term electric field. So an electric field is a region in space in which a charge will experience an electric force. So it is a region in space in which charge will experience an electric force. That is an electric field. So now, electric field is a region in space in which an electric charge will experience an electric force. straightforward. So an electric field, it is a region in space in which an electric charge will experience an electric force. So that force can be attraction, can be repulsion. So that's what an electric field is. It is a region in space in which an electric field, an electric charge will experience an electric force. So let's go to the next question. Calculate the magnitude of the electric field at point M. So they want us to calculate the magnitude of the electric field at point M here. What is the size, the electric field strength at point M? They want us to calculate that. What is the electric field at point M there? That is what they want to do. So in order to tackle this question, you must find the electric field experienced at M as a result of A, and the electric field experienced at M, at point M, because of B. That's what you should do. I'll repeat this again. So, in order for you to be able to answer this question, to find the strength of the electric field, the net electric field at M, you must first find the electric field experienced at point M as a result of A, and the electric field experienced at point M as a result of B. Then once you've done that, you can be able to find the net electric field strength at that point. So let's go. So what I think I will need, okay, so now we know that M is negative. So the electric field lines at A are moving inwards because it's an R. I'm moving inside A because A is negative. So the electric field lines at A are inwards because A is negative. So the electric field experienced by M as a result of A will be towards A, which means now if you were to draw some sort of a force diagram or a field diagram at A, you would find that the electric field experienced by M as a result of A is in that direction. So this is the electric field of A on M. So M is experiencing experiencing an electric field of A to that direction, which is to the left because of A. Because A, the electric field lines are going into A, which means now if your M is here, the electric field that M will experience will be towards that direction. That's why there is the electric field on M as a result of A is on that side. So now when you calculate now the electric field, when you calculate the electric field, experienced by M as a result of A, you know its direction will be towards this direction, which is, I would say, it's your left. It's towards the left. It should be on your left, this direction. So now, let's go and calculate the experience. Let's now go and calculate the electric field experienced by M as a result of A. That's the first step that you should do. So now, what is our equation for the electric field? 7.4. electric field is equal to force over this. Then you know our force is K, Q1, Q2 over Q. This and this go away. Oh, sorry. R squared. So now, cause this is column, this part. So what do you have? You have K, Q over R squared. This is our formula for electric field. So now we are calculating the electric field of experienced by M as a result of A. So electric field of A on M is equal to K, which is 9 times 10 to the 9 times our charge of A, which is 4 times 10 to the power minus 6, divided by R squared. What is our R? R is the distance between M and our charged sphere A. So what is the distance between the two? The distance between M and A is 0.2 plus 0.1, which is now the distance between from A to M is 0.3 meters. So it's the distance between your charge and your point, which is on your electric field. So now the distance between the two is 0.3 meters. So now what you're going to do is, okay, the distance is 0.3 meters squared, which is equal to electric field of A on M is equal to 9 times 10 to raised to the power 9 times 4 times 10 raised minus 6 divided by 0.3 squared. So this is 4100 times 10 to the power 5. What are the units? So electric field is force over charge, which is newtons, over column. This is Newton, this is a column. And this is to the left, because we said that this electric field is to the left. Why is that? Because we said that the electric field that will be experienced by, okay, let me go back to the diagram again. So I'm saying this will be to the left. This will be to the left. The reason it's to the left is because, let's go back to the diagram. We said that M is sitting here, right? And A is negative. So the electric field lines are inside A. They are inside A. So now the field that will be experienced here, it will be towards this direction. It will be pulled by A. So take this one is, assume that it's not there. Don't look at this charge here. Look at one charge at a time. Look at this one alone. So now if you have A here and you have a point here, which is M. So M will experience a field to the left because of A, because A is pulling everything to this direction. So it will be the electric field experienced by M as a result of A, it will be to the left. So now we do a similar calculation for B. We look at B. B is positively charged. B is positively charged, which means the electric field lines are going outwards. like this. So now, if you say this, the electric field experienced by M as a result of B will be towards that direction, because you see these are pushing to that direction. So now, it will be in that direction. So this is the electric field of B on M. It is to the right. So because this B is positive, so the electric field lines are outwards. So if you have a point sitting here, the electric field lines to be feeling will be towards that direction. So it is to the right. So now you will do the similar calculation to calculate the electric field strength at M as a result of B. Then once you get that, you find the net between the first calculation and the second calculation. So let's do that. So okay. Let's say okay, we have E is equal to K Q over R squared. K is 9 times 10 to the power 9 times this, which is 3 times 10 to the power minus 6 divided by 0.1 squared. So E, electric field strength at M, or electric field strength at M, okay, electric field of B on M is equal to whatever answer that you'll be getting here. So it will be 9 times 10 raised to the power 9 times 3 times 10 raised power minus 6 divided by 0.1 squared. So what do we have? We have 2.70 times 10 to the power 6 newtons per coulomb. Okay, so this is what we have, and this is to the right, this one here. The first one was to the left, the first one. So what was the first answer? So the electric field of B, of A on M was this, to the left, and the other is to the right. So now we have these two electric field strands, which is, you have your M here experiencing this direction, electric field to this direction and to that direction. This is the electric field of A on M, electric field of B on M. So the other one is 4.00 times 10 to the power 5 newtons per coulomb. The other one is, what is it? 2.70 times 10 to the 6 newtons per coulomb. So now, if you want the net, just add the two. The one is to the right and the one is to the left, the other is to the right. So you can say your right is positive. So net, E net is equal to this 2.70 times 10 to the minus to the power 6 plus the negative 1, which is going to the left, 4.00 times 10 to the 5. Final answer is 2.7 times 10 to the 6 plus negative 4 times 10 to the 5. What do you get? Get 2.3. Get 2.30 times 10 to the 6 newtons per coulomb, which is positive, which means now this is to the right. Finish this question. This is how you do it. So the most important thing here is to be able to identify how the point is influenced by each electrically charged sphere independently. So look at one sphere at a time and see how that point will respond to each sphere. Don't look at them at the same time. You will be confused. Then let's go to the next question. So now we're going to read the next statement. They are saying charged spheres A and B and another sphere D are now arranged along a rectangular system of axes as shown on the diagram below. So I'm going to draw this. So I think it's important. Okay, now let's proceed to the next question. So charged spheres A and B and another sphere D are now arranged along a rectangular system of axes as shown on the diagram below. So we had A and B, so now we had D is placed over there on this rectangular system of axes. So now let's read the next. Let's continue reading. The net electrostatic force experienced by sphere A is 7.69 newtons in the direction shown in the diagram above. So now, because we have sphere D here, the net electrostatic force at point A is this magnitude in that direction. So we know A is negative, B is positive, right? We know this from the previous question, right? Yeah, we know this from the previous question. So now, A is experiencing an electrostatic force, a net electrostatic force of 7.69 in that direction. This is what we're told. So let's continue reading. Is D positive? Is the charge of sphere D positive or negative? They are asking us if D is positive or negative, right? So now when we did the first calculation, we established that the force between A and B is attraction, right? Which means now B was the force experienced by A as a result of B is in that direction. Which means now A, if we draw the flipboard diagram of A, yes, let's say we have A here. We're drawing the flipboard diagram of A, right? So, the flipboard diagram of A. So now we know for sure that A, the force experienced by A as a result of B is in that direction. So A is being pulled in that direction by B. So I'm not going to include the force of gravity and the normal force of the stance, but the force I'm only going to draw the force that we're interested in, which is our electrostatic forces. That's the only forces that I'm going to focus on here. So now, so this is the force on A by B. So this is the force felt by A as a result of B. It's attraction in that direction, right? And then now, if we have D here, if D is positive, which means now the forces between these two will also be attraction, which means now A will be pulled up in that direction. So now if A is pulled in this direction, which we know already, and also pulled in that direction already, which means it's going to move towards that direction because it's being pulled by both of these electrically charged spheres. I'll repeat this. So let's say D is positively charged. So if D is positively charged, what does that mean? This tells us that A will experience an attraction which is in that direction, right? And also experience another attraction which is in that direction. Which means now your sphere is pulled in this direction and that direction. The resultant force will be in this direction, which will be this. So D should be positively charged. But now let's assume that, let's say, for argument's sake, D was negatively charged. So if D was negatively charged, that means the force between D and A will be repulsive, which means now B, which is B, I'll draw another football diagram. So this is A here. So A will still be experiencing the attraction force, which is that direction. This is A here. The second force, it will be a repulsion of D if D was negative, like A is. Which means now that repulsive force will be down here. And the resultant force was going to be in that direction. Or the net force. So you can't have D as negative, because if D is negative, which means now we'll have a repulsive force between the two. And A will be feeling the repulsive force, which will push it downwards, like this, and the resultant will be that one. But if D is positive, it attracts B, it attracts A, which will force it to go up like it does there, and the resultant force is in that direction. So D should be positive. So is the sphere D positive or negative? So D is positive, which is 67.5. D is positive. Let's go to the next question, which is 7.6. How does 7.6 read like? Calculate the magnitude of sphere D. They want us to calculate the magnitude of sphere D. So they want us to find what is the magnitude of this sphere here. How do we do this? We say, okay, to do this, to do this, which is calculate this, the magnitude of sphere D, we say, okay, we have the resultant force to be this here, right? So and we know the force between A and B, that it was 2.7 newtons between A and B. So we know we want this vertical force. We know the horizontal force. We know the resultant force. We want this vertical force here. So we can find this vertical force using Pythagoras theorem. Because we calculated this in the first question, to be 2.7 newtons. We were given the resultant force, or the net force of A as a result of the influence of D and B as 7.69. So what we want now, we want this force here. To find this force here, actually we want the charge of D. But to do this, we need to find this force that we have here, right? So now we can use Pythagoras theorem to find this vertical force, which is okay. We can say, okay, r squared is equal to x squared plus y squared. R squared is our hypotenuse there, 7.69. Squared is equal to x squared, 2.7 squared plus y squared. So y is equal to, can solve this, 7.69 squared minus 2.7 squared. So what do we have? We have that our y is 7.20 newtons. This is our force between. So this is equal to the force between what? This is the force between A and D, right? And then now we know that the force between A and D is equal to K Q1 Q2 all over R squared, right? So we do have the force. What is our force? It's 7.20 is equal to K, which is 9 times 10 to the 9, times Q1, which is what we don't have, times Q2, which is what we have. 4 times 10 to the minus 6, all divided by the distance between them. Square of a distance, which is 0.15, all squared. From this, we are solving for Q. This times that, then divide by this product here. So you say 0.15 all squared times 7.2 divided by the product of this and that. So you find that your Q is equal to 7.2 times 0.15 squared divided by 9 times 10 to the 9 times 4 times 10 to the minus 6. So it's 4.5 times 10 to the minus 6 coulombs. And say 50. So this is our charge for D. So we know that D is equal to 4.50 times 10 to the minus 6 coulombs. So this is how you do this question. This is how you should have chowed, or you can chow this 17 marks. So I'm going to stop there. Cheers.